Hello, welcome to lesson 34. So let me scroll this up just a little bit. Okay, so yes, this is a typo. This is actually lesson 34, and we are going to cover section 4.4 from the textbook talking about ANOVA. So you are encouraged to read pages 184 to 195 in the textbook. So to test whether observed differences in means could have happened just by chance, even if there was no difference in the respective population means, we will use the F statistic and ANOVA. The method of analysis of variance in this context focuses on answering one question: is the variability in the sample means so large that it seems unlikely to be from chance alone? So remember that with this type of hypothesis test, the null hypothesis will say that all the means are equal. And the alternative hypothesis will say that at least one mean is different from the rest. So this question is different from earlier testing procedures since we will simultaneously consider many groups. And we will evaluate whether their sample means differ more than we would expect from natural variation. We call this variability the mean square between groups, or MSG. And it has an associated degrees of freedom of df equals k minus 1, where there are k groups. So this is very similar to chi-square. It's very similar to the chi-square process. So if we have a large mean square, if we have a large variability of the mean square between groups, or a large MSG, not monosodium glutamate. So if we have a large MSG, that means that the box plots are spread out. And if we have a small MSG, that means that the box plots are close together. Graphically, the MSG can be thought of as a measure of how well the groups overlap. If the graphs more or less overlap, then the null hypothesis is plausible and any variation in the sample means is likely due to chance. The formula for MSG is this. So MSG equals SSG divided by DFG. So let me define what those are. So SSG is the sum of squares between groups And the DFG is the degrees of freedom oh my goodness. Freedom of the groups. And remember that that is calculated by taking the number of groups minus 1, or k minus 1. Fortunately, we will use calculators and software for these computations, so we will not be doing this formula over here on the right. That looks pretty complicated, although we could do it by hand. We will allow our calculators and other software to do it for us. The mean square between the groups is, on its own, quite useless in a hypothesis test. We need a benchmark value for how much variability should be expected among the sample means if the null hypothesis is true. To this end, we compute a pooled variance estimate, often abbreviated as the mean square error, or MSE, which has an associated degrees of freedom value that is equal to n minus k. So that would be the sample size minus the number of groups. It is helpful to think of MSE as a measure of the variability within the groups. So the formula for MSE is SSE divided by DFE. So let me write some things in here. So SSE represents the sum of squares for the errors, and the degrees of freedom, so DFE, is the degrees of freedom associated with the errors. And we calculate that using n minus k, so the sample size minus the number of groups. So MSE, so the measure of the variability within the groups, the measure of the variability within the groups is, when we saw in a previous lesson, how long are the box plots. That's measuring how long they are. So the longer they are, the more variability there is. So when the null hypothesis is true, any differences among the sample means are only due to chance. And the MSG and MSE should be about equal. As a test statistic for ANOVA, we examine the ratio of MSG and MSE. So F is our test statistic, and it's calculated by dividing MSG by MSE. So it's basically saying the treatment effect divided by the measure of precision. So the MSG represents a measure of the between group variability, and MSE measures the variability within each of the groups. So the treatment effect, what is that? This is a measure of how well the box plots line up. What is the measure of precision? This means how long are the box plots. So both of these together form our test statistic, which is F. So we take the treatment divided by the precision, and this equals the test statistic. So here are our different formulas for the degrees of freedom. The total degrees of freedom will be the sample size minus 1. The degrees of freedom for the groups will be the group number minus 1. So the number of groups minus 1. And the degrees of freedom for the error will be the sample size minus the number of groups. So the total is equal to the other two added up. Last lesson, we considered whether there are real differences between the batting performance of baseball players according to their position: outfielder, infielder, designated hitter, and catcher. To answer this question, we considered the on-base percentages, or OBP, of 327 Major League Baseball players from the 2010 season. Here's example 1. For the baseball data, MSG equals 0.00252, so that's given to us, and MSE equals 0.00127, also given to us. Identify the degrees of freedom associated with MSG and MSE, and verify the F statistic is approximately 1.984. Okay, so the degrees of freedom total will be the sample size, 327, minus 1, which is 326. The degrees of freedom for the groups will equal the number of groups, which is 4, minus 1, so that equals 3. So again, this is the number of positions minus 1. The degrees of freedom for the error will be the sample size, 327, minus the number of groups, which is 4, so that equals 323. And you'll notice that the degrees of freedom for the groups and the degrees of freedom for the error, they add up to 326, which is the total. Let me write that a little bit better. Okay, and so now let's verify the F statistic, or the test statistic. F equals, we're going to take the MSG, so 0.00252, and divide it by the MSE, 0.00127. So if we type that into the calculator, we get approximately 1.984. So it works. It is true. So FCDF is found on the TI-84 calculator. Once again, if you don't have one, that's okay. I have built-in calculators in the homework problems. So FCDF computes the F distribution probability between lower bound and upper bound for degrees of freedom in the numerator, which is the groups, and the denominator, which is the error. So what we would do is we would use FCDF in our calculators, and A is the lower bound, B is the upper bound, and then we would write the degrees of freedom for the groups and then the degrees of freedom for the error. And this is going to give us the area under the curve between those 2 points, or in other words, the probability that a randomly selected data point would occur in that range. So, like the chi-square test, the p-values for ANOVA are calculated using the right tail only. So we would use FCDF, and then we would put our test statistic in, comma, a big number, and then our degrees of freedom for the groups and our degrees of freedom for the error. And you can see this is how the tail would be shaded by doing that. So here's example 2. Compute the p-value if f is 0.67, degrees of freedom for the groups is 4, degrees of freedom for the error is 32. So on the calculator, on a TI-84 calculator, you would go second and then your vars button, which is the distribution button, and you would scroll all the way down to FCDF. Okay, so that's what we're doing here. So FCDF, and then we would put in 0.67, comma 999, comma 4, and then 32. And this should give us a p-value of about 0.618. For part B, we would use FCDF. We would put in 12.9 and then 999 for the upper bound, and then 7 and then 98. And this gives us a p-value of about 1.175 e negative 11. So remember, if you see a display like that on the calculator, this is the same as scientific notation. It's 1.175 times 10 to the negative 11 power. How many groups and how many observations were included in each part above? Well, in part A, there were 5 groups, because if I take the degrees of freedom and add 1, I get 5. And there were 37 observations, because if I take the degrees of freedom 32 and add 1, I get 30. If I take the degrees of freedom from both parts, 32 plus 4, and then I add 1 to that, I get 37. So that's the total. The total degrees of freedom plus 1 gives me the total observations. Part B, I know that there are 8 groups. Because I take the degrees of freedom 7 and I add 1 to it, I get 8. I also know that there are 106 observations, because if I take the total degrees of freedom, 98 plus 7, and add 1 to that, I get 106. Here's example 3. The test statistic for the baseball example is F equals 1.984, with degrees of freedom for the groups of 3 and degrees of freedom for the error 323. Shade the area corresponding to the p-value and then compute the p-value using the FCDF command. Does this provide strong evidence against the null hypothesis? So if I mark off, so this part is 0 where the graph starts. So I'm just going to guess 1.984 is maybe about here. So I would shade in the right tail. and this would be my p-value. So if I use fcdf command, then I start with 1.984, comma 999, comma 3, and then 323, and I get about 0.116. So because this is greater than our significance level of 0.05, we would fail to reject the null hypothesis. Okay, now sometimes we might have actual data that we need to use instead of just the data summary. And if that happens, we can use our calculators to type in the lists. Again, if you don't have a TI-84 calculator, I do have built-in calculators that will do this as well. But in the calculator, what you would do is first enter data into a bunch of different lists. And if you're wondering where the lists are, they are located in the Stat button. So if you want to put lists in, you go to Stat, and then you go to Edit, and that's where you can type in all the different lists. So type in values for the lists. Okay. After you do that, you'll go back to your Stat button, you'll go to Tests, and then you'll go to ANOVA. So if you go to Stat and then Tests, ANOVA is at the very, very bottom. It's option H. So it's at the very end of the list. End of the list. Okay, that's where ANOVA is. Once you select ANOVA, it will show up on your calculator screen as ANOVA with a open parenthesis, just like it says here. So it's at the end of the list, so H, it's at the end of the list, then it'll type ANOVA on your screen. And what you're going to do there is you're going to type in all of the list numbers separated by commas. So you can find L1, L2, L3, L4 by going second, like clicking your second button, and then choosing the numbers 1 or 2 or 3 on your actual calculator. So your actual calculator buttons that are 1, 2, 3, 4, 5, 6, those have your list numbers right above them. Okay, so that's where you'll find it. After you do that, you just press enter, and then you'll be able to see all of the summary data for that. So example 4 is going to have us practice that. So it says below are the commuting times for randomly selected drivers in 6 cities. Test whether the average commuting times are the same. So again, we're going to put all of this data in to list 1, list 2, list 3, list 4, list 5, and list 6. So to do that, you would go to Stat and then Edit, and you would enter in all the values, and then you would go to Stat and then Tests, and then scroll down till you find ANOVA at the bottom, and then you're going to have ANOVA on your screen with an open parenthesis, and then you're going to type in L1, comma L2, comma L3, and so forth. Close the parenthesis, hit enter, and then the F is your test statistic. The F value that it gives you is the test statistic, and it should be about 0.75. And the P is the p-value, and that is about 0.59. And so because 0.59 is greater than the significance level of 0.05, this means that we would fail to reject the null hypothesis, meaning that it's probable that there is no difference in the means of commuting times.